Okay, welcome to the videos for topic 3 for week 10. So as per my previous videos and the discussion at the workshop and so on, this topic is smaller. We had a big one on topic 1, so that's the focus for the week. In terms of the bulk of your time will be spent understanding calorimetry and how to solve heat problems, both specific and latent heats, and all of that information. That is the more difficult part of the week. Yesterday's topic, or topic 2, was on conduction and convection. We did have some equations for conduction, but fairly simple, no real curveballs in there. Convection is just qualitative. We don't talk about any equations or numbers, just the idea of convection. And today we'll look at radiation, and radiation will have some equations in it, so we are going to look at some equations, but again, like we did with conduction, they'll be fairly straightforward, fairly simple ones, just to get an idea and appreciation of the topic without going as much into depth as we did for, say, calorimetry in detail earlier. So we'll jump over to the lecture slides and we'll get started. Radiation, week 10, lecture 3. That's not what we want. Here we go. Okay, so the learning outcomes for today. We've got to define thermal radiation. We've got to be able to calculate heat flow rate and net heat flow rate due to thermal radiation. And we have to define emissivity and relate it to emission, absorption, and reflection. So not too much to go through, just a few topics related, a few concepts related to the topic of radiation. No matter. We looked at conduction and convection, and both of those required material, physical particles, to transfer that thermal energy. In conduction, they were all stuck in place because it was a solid, and each particle bounced into its neighbor and gave it some energy. So we saw conduction occurring. Conduction can occur in non-solids as well. The solids are just the simplest example because they're actually stuck in place. In a liquid, they can still conduct from one to another, but obviously they're moving around at the same time. And that brings us over to convection, which is where the heat transfer is occurring because the particles themselves are physically moving. So if they've got some heat energy and they are some thermal energy from heat, and then they move away, that thermal energy is moving, and since heat is the flow of thermal energy, we have heat going on. We have heat flow. But what happens when there's no matter? Between the sun and Earth, we have no matter, we have space, it's empty. Officially, it's not quite empty, but for our purposes, it's empty. So there's essentially a vacuum between the Earth and the sun. Yet somehow the energy from the sun gets all the way to the Earth without any problem. Right? If it didn't, it wouldn't be very good. We'd all be dead, or we never would have existed in the first place. But it does get here, and it comes from radiation. Radiation is energy that is emitted by the atoms and electrons making up an object. So remember that everything's made up of atoms, and atoms have electrons in them. You may or may not have met the composition of atoms yet. We're not too worried about all of that. But the point is all those little particles have a bunch of thermal energy, and they just give it off. They just give out some energy. They just throw it away. And the way they throw it away is in the form of radiation. So as opposed to giving the energy to another particle, which is what we saw with conduction, or taking it and carrying it somewhere else, which is what we saw with convection, in radiation, they just throw the energy away into open space, not into another atom or anything else. And that packet of energy, it just travels through anything. It will travel through empty space, or it can travel through other materials, in between atoms and things of other materials, and get through some substances. When it does actually hit another particle, that other particle can absorb it, and then it gains that heat. So the heat has come from some atom or molecule. It's been sent as a little packet of just energy, no matter, through space or through whatever, and then it gets hit by something else, and that thing collects it, and now it's got some energy that was originally in the thing that emitted the radiation. Radiation generally takes the forms of electromagnetic waves. Visible light is one type of electromagnetic wave, or EM wave. There are many more. There's a whole big spectrum of them, and visible light is a tiny part of it. At this stage, we're not going to concern ourselves with what electromagnetic waves are or how to deal with them or talk about them, but we did want to give you the name electromagnetic wave just so that you can be aware of that. And that means that light, visible light, is one of these forms of thermal radiation. Indeed, the sun, as you can all see, when you look at the sun, you can see visible light. That is thermal radiation coming off the sun. So how quickly is an object giving off thermal radiation? How much energy does it throw out into the environment around it? It turns out that that is given by this equation, the Stefan-Boltzmann equation, the rate of heat flow, so delta Q by delta T. So remember, delta Q is the amount of heat, delta T is the amount of time, so delta Q by delta T is the heat per unit time, or the rate of heat flow. And that is given by these four terms. We've got epsilon, which is the emissivity of the object. We'll talk about that in a moment. Sigma is just a constant, the Stefan-Boltzmann constant, which is given there on the lecture slide. A is the surface area of the object. So the surface area is obviously the part of the object that can actually radiate. If an internal part of the object radiates, it'll just immediately hit another part of the object. So that doesn't give off any radiation to the environment. But the surface area, the particles that are all on the surface of the object, those are the ones that can radiate some energy that will be sent out into the environment. So that's the relevant factor of the physical dimensions of the object. And it turns out that it's proportional to the fourth power of the temperature. So epsilon sigma A T to the fourth power. That was just discovered through testing, through empirical analysis. We did a bunch of measurements, not we. Again, I always say we, it sounds like I'm including myself. Obviously, I wasn't involved, but the scientists who did it discovered that it was the fourth power. So emissivity, that little epsilon term, that's the difference between two objects based on what they're made of. So you can have two identical objects in terms of their dimensions, their temperature, and so that would give us the same A, the same T, but if they've got a different emissivity epsilon, then they will have different rates of heat flow through radiation. And it's just a value that ranges from 0 to 1. So 1 is the maximum amount that it could give off, and 0 being giving off none. And it tells us how good a material is at turning their thermal energy, their internal energy, into radiation. How much of their internal energy are they going to be able to throw away as radiation off to the environment? It turns out that very dark and black materials are good at giving off radiation, while reflective ones, so silvers and shiny things, they're not so good at it, and they'll get epsilons closer to 0. So a very crude little diagram. You've got two similar objects, one's black, one's reflective silver. Then the black one will give off a lot more thermal radiation than the silver one will, provided they're at the same temperature and they have the same dimensions and everything else. So that's all emissivity is telling us. Right? It's saying for some object at a given temperature with a given surface area, how good is it at actually throwing away that thermal energy? The higher the epsilon is, the closer to 1 it is, the more it'll be giving off. Now, the important thing to note is that everything is constantly radiating energy. Any matter at all that has some thermal energy will radiate some of that energy as heat. How much it radiates depends on its surface area and its emissivity, as we just saw, but it will be giving off some. Right? That means that everything always is giving off radiation, because everything always has some temperature. Even lab results, we get down to tiny little amounts of Kelvin, tiny amounts of Kelvin, but we never actually get to 0. Absolute 0 is theoretically not a temperature you can really reach. Everything always has a tiny amount of energy. We're not going to worry about those really cold temperatures because it gets a bit messier. But in general, especially in everyday life, everything has thermal energy. Our entire world exists in the range of sort of 250 to 350 Kelvin. Right? That's our standard everyday life. Actually more like 370 for boiling water. But anyway, so we've got this range of Kelvin. So everything that we encounter on a daily life has over a couple of hundred Kelvin in terms of its temperature. And that means that it's going to be radiating energy. So everything you encounter everywhere, all the time, forever, will always be radiating thermal energy. Everything in this photo is radiating thermal energy. Right? I could have used any photo of anything anywhere. That's the point. Anything at all that has a temperature, which is everything, will be radiating thermal energy. How much it radiates depends on those properties that we were talking about. So where does all this energy go then? Everything in the universe is radiating some thermal energy. It's just constantly going out. Everything in your room, if you look around your room now, everything is radiating some thermal energy. So where is that going? These little packets of energy are flying all over the place. Where is it? Well, we said that it gets hit. When it hits something, it will get absorbed. And the thing that it hits will gain that thermal energy. So what's absorbing it? Everything. Everything is also absorbing thermal energy. So thermal radiation is just this constant exchange of energy between everything. Everything's radiating energy according to the Stefan Boltzmann equation that we saw, and then everything is also absorbing energy at a similar rate. So how does absorption work? Well, it turns out that things that are good at emitting are also good at absorbing. It's the same thing. That emissivity that we saw is the same for absorption and for emission. So a good absorber will be a good emitter, and a good emitter will be a good absorber. Whereas the low epsilon, the close to zero reflective civil we saw that was a poor emitter, that will also be a poor absorber. So I've drawn here only 3 arrows for the sake of simplicity. We've got 3 arrows approaching our good absorber, and all 3 get absorbed. They all just stop because the energy's now been absorbed. But on the reflective silver block, we've got 3 arrows coming in, which is 3 radiations, which isn't a real thing, but we've got 3 coming in. 1 of them gets absorbed and 2 get reflected. So that actually wouldn't be that close to zero because it's absorbed a third of the radiation, which is still quite a bit. But the idea is it's a lot less than the black object. So that's absorbing some. The good absorber is absorbing all of it. Now suppose we've got an object sitting at some temperature T1, and it's sitting in a room. The room and everything else in the room is all at some other temperature T2. Then everything else in the room is radiating thermal energy based on its temperature T2. Right? Remember that it was proportional to the 4th power. So everything else in the room is radiating energy at a rate proportional to T2 to the 4th power, while the energy the object itself is radiating is proportional to T1 to the 4th power. So that means that the object is absorbing radiation from other things at a rate of T2 to the 4th power, but emitting from itself at a rate of T1 to the 4th power. That means that if its own temperature is higher than the surrounding temperature, it'll be emitting more radiation than it's absorbing. Right? If it's the other way around, if we've got T1 less than T2, then it will be absorbing more than it's emitting. So the hotter temperature object will emit more than it absorbs, but a colder one will absorb more than it emits. And that should hopefully be no surprise, because what that means is that the net flow rate, right, the net flow rate is just the same formula we saw before, but now instead of just the temperature to the 4th power, we have the difference in the 4th powers of the temperatures. You'll note that I've put T2 as the first temperature and T1 as the second one. I've got T2 to the 4th minus T1 to the 4th. In the textbook, it's the other way around. I prefer it this way around because if we do it this way, our convention that we met earlier where we said a negative heat flow rate is going to be the object losing heat. Remember we said negative heat is the object has lost it, because the object is our system in this case, whereas a positive heat means the object has gained it. So by putting it this way around, it just adheres to that. But the textbook, as I said, has it the other way around. It doesn't actually matter too much. What we're concerned with is the heat flow rate as a numerical value, the magnitude of the heat flow rate. And we should always be thinking about the system. So we should already know, just based on the temperatures T1 and T2, which way the heat is flowing. If the object is hotter, it'll flow out of the object. If the object is colder, it'll flow into the object. So that should be no surprise. But by writing the equation this way, it does adhere to that convention that we met earlier. So that is the net heat flow rate. The delta Q by delta T is equal to epsilon sigma A, and then the difference in our 4th powers of temperatures. When an object is at thermal equilibrium, so thermal equilibrium, we've already met that concept, it just means at the same temperature, right? So when the object is at the same temperature as the surrounding environment, then the net heat flow rate must be 0. This is confirmed by the equation we just saw. I'll go back, this equation, T2 minus T1, right? Both to the 4th power, but we're talking about the difference of 2 of the same number. Right? If those are at equilibrium, those are the same number, and so the difference is going to be 0. And so we have a net heat flow rate of 0. Right? So there's still absorption and emission going on, but it means that the amount that's being absorbed is the same as the amount that's being emitted. Now, at thermal equilibrium, an object will absorb more and emit more if it's a good radiator and a good emitter / good absorber. But if it's a poor radiator, then it'll still be absorbing and emitting the same amount, but it'll also be reflecting a bunch, right? So this is just like we saw before. This black object is a good emitter, therefore it's a good absorber, and therefore it's a poor reflector. So we're getting no reflection going on. We're getting all the 3 arrows that are coming at it get absorbed, and then it emits 3 as well. So it's emitting just as much as it's absorbing. The good reflector, which is a poor emitter and a poor absorber, it reflects 2 out of the 3 arrows coming in, 2 out of the 3 radiations coming in. It absorbs 1 and it emits 1. So both of them are at thermal equilibrium because they're absorbing the same amount as they're emitting, but we've still got this difference in the actual amount that is being absorbed and emitted throughout time, over time. Humans are constantly radiating. We are radiating, you are radiating, I'm radiating, everyone's radiating all the time. I was about to say throughout their life, but always, because even after death, humans might be colder, but they're still not absolute zero. But that's a morbid topic. So human bodies are usually warmer than our environments when we're alive. So that means that we're actually radiating more than we're absorbing. We just said that an object that's hotter than its environment will be net radiated or net loss of energy. So that means we are net emitters. We are always emitting more thermal radiation than we absorb. If we emit too much, then we feel cold. Right? And if there's a big temperature difference between the environment and us, then that net heat flow rate will increase and we'll lose lots of energy and we'll get cold. So we'll put clothes on or we'll turn a heater on to warm up the environment. So we've got ways to try and minimize that temperature difference. And actually, wearing clothes is a good example of bringing back the conduction, right? Where by putting a jersey on, the heat is now no longer being radiated just directly from your skin to the environment. It has to go from your skin into the jersey, has to be conducted through the jersey and then out the other side. But jerseys trap a lot of air in them, or at least good ones do. They trap a lot of air in them, and as we saw, air is a really poor conductor. So that energy that reflects off, radiates off your skin onto your clothing has a hard time getting through the clothing so that it can be radiated out into the environment. So by wearing clothes, we're actually bringing in a whole bunch of different heat mechanisms to try and prevent heat loss. On the other hand, if we don't emit enough energy, then we will overheat. If we are in a very hot environment, our body can't radiate enough to cool us down and we would overheat. So obviously, again, we can take steps. We can get ourselves into an air-conditioned room so that we now have a colder environment, or we can increase the exposed skin surface area so that we can radiate more, and so on. So there's various steps we can take to try and cool ourselves down. Where does energy come from on Earth? Well, most of it comes from the sun. The sun is our giver of energy. It's a massive hot star located about 8 light minutes away from Earth. Not necessarily that massive or hot on a universal scale, but certainly for us, as tiny little humans, the sun is very large. It is 8 light minutes away from Earth. That means that light takes 8 minutes to travel the distance from the sun to Earth. And the thermal energy from the sun cannot travel to Earth by conduction or convection. This is what we started this topic out by talking about. It's all coming to us from radiation. Right? All the energy the sun gives off is in the form of radiation. There's no conduction or convection because there's no matter in space. So it emits some electromagnetic waves, and then 8 minutes later, some of those hit Earth. Not all of them, just some of them, because the sun is emitting in every single possible direction all the time, right? And so the heat is just flowing away from it as electromagnetic waves in every direction at equal rates all the time, everywhere throughout space, in a bubble around the sun, just expanding. And we're only a tiny little pinprick. Right? We're a tiny little Earth, we're a little dot sitting ages away from the sun. So by the time all the energy from the sun has been sent that far, we're only catching a tiny little amount of it, right? So we're actually only getting a tiny, tiny fraction of the energy that the sun gives off anyway. But that tiny, tiny fraction of the energy is enough to support all life on Earth. Right? That's where our energy comes from. The plants, absorb the sunlight through photosynthesis. They turn it into energy that they store inside their cells. And then animals go and eat those cells and get energy from that. And then we eat the plants or the animals or whatever we choose to eat and get energy from that, and so on. And so all that energy coming from the sun, the tiny fraction of that we catch on Earth, is enough to support all life on Earth. Thanks, sun. Energy rate from the sun, how much is it actually giving us? Well, we can't use the net heat flow rate. I just realized that slide says net heat flow rate, which is nothing. So we can't use the net heat flow rate equation that we saw earlier because the sun is a point source. It's not an environment that's encapsulating us. We talked about an object sitting in an environment, the environment being at some other temperature. That's not true for the sun because we're not in it. We'd be dead. We're not in the sun. We've got the sun as a little point source, and we're just catching some of the radiation that it gives off, as I was saying. By the time that radiation from the sun does reach Earth, if you draw 1 square meter directly facing the sun, that 1 square meter of area at Earth's position away from the sun would catch 1,350 watts per square, 1,350 watts per square meter. I've already been saying square meter. That's called the solar constant. So the solar constant is a very human-centric term. It's the amount of energy that that passes through 1 square meter at Earth's position from the sun every second. But of course, on Earth, we're not a cube. We're not a flat surface facing the sun, despite what some people might think. We're not a flat surface facing the sun. We are a sphere. And that means that your position on the sphere determines your angle to the sun. You're not always, the ground isn't always facing the sun directly. So if the sun's over here, the ground isn't always perpendicular to that sun ray, that sunlight that's coming towards us. And so if the ground is at an angle to that sun ray, then that means you're actually going to be getting slightly less because the solar constant is based on a perpendicular square catching that sunlight. If you tilt your square, you're now not going to catch as much of it. And so that's just simple trigonometry. It tells us that we have to bring in this factor of cos theta, cosine theta, where theta is your angle from that perpendicular. So that perpendicular is our solar constant definition. If you tilt some angle theta away from it, either way, then your amount of energy that you're getting is reduced by a factor of cosine theta. Furthermore, that's the amount of energy that makes it to the Earth, but it's not the amount that makes it to the ground, because to get to the from space to the ground, you've got to go through a whole bunch of atmosphere, and as you do so, all the particles in the atmosphere will catch, they'll absorb some of the energy from the sun, some of that radiated energy. On a clear day, we can end up with 75% of it reaching Earth, or 25% being absorbed by the atmosphere, roughly. Very approximate terms here. But on a cloudy day, clouds are made of tiny water droplets. Water droplets are quite large, and so there's a good chance that the light coming through, the radiation from the sun coming through, will hit one of those water droplets in the cloud, and that water droplet will absorb the energy. And so those clouds can actually catch a whole bunch of that energy from the sun, and it means it doesn't all make it to the ground. And they can catch as much as 70%. Well, we can lose as much as 70% through the atmosphere and the clouds when there is a lot of cloud cover. Obviously, that energy is still being absorbed somewhere on Earth, but it's not making it to the ground, which is where we would catch it with our solar panels, or where plants and other animals would absorb that energy instead. So we have to account for that tilt off the perpendicular solar constant definition, and we have to allow for some of this energy being absorbed by the atmosphere. So what we do is we bring both of those terms in, and we say that the rate of heat from the sun is going to be around about 1,000 times A, the surface area. Remember, we said 1,000, we said 1,350 per square meter. We're saying let's lose some of that on the way from the atmosphere, so let's say it's only 1,000 now, and then it's 1,000 per square meter, so we've got to multiply by the area of whatever we're considering. We'll put an A for that, and then cosine theta to allow for the tilt away from our defined perpendicular plane. And that will be the amount of energy that hits some object of area A due to the sun. Then we have to allow for how much it will actually absorb. So we have to bring in that emissivity. Remember, the emissivity is both emission and absorption. It's how much it emits and absorbs out of the power that it's being, the heat, which is heat per unit time, is power that it's receiving. So in this case, the absorption by an object of area A of emissivity epsilon at an angle theta relative to the perpendicular is going to be given by 1000 epsilon A cosine theta. Now remember that 1000 is an estimate based on the atmosphere absorbing about a quarter of the energy that comes from the sun. So on a really cloudy day, that's going to be less. Now let's think about the seasons. The Earth itself is actually tilted. It's not always facing the sun in the same direction. As you can see from this angle, we've got the equator going at a slight angle. The axis is marked on. The Earth is spinning around this axis, so that equator stays where it is, but it just rotates around in that direction. That means that this top half, the top half here where it says summer, theta equals 0, this bit is facing the sun directly. So it gets the full amount of that solar constant. But by the time we get all the way up to the North Pole, we're getting a lot less. And if you go down to the southern hemisphere, then by the time you get a similar distance down, so up here you're only at slightly off perpendicular. By the time you get to the southern hemisphere, you're already off perpendicular. So the southern hemisphere is getting a lot less energy. The northern hemisphere getting most of it. So that's going to make it summer in the northern hemisphere. They're getting more sunlight hours, more energy, and winter in the southern hemisphere, where they're getting less sunlight hours and less energy. And by the time you get around to the North Pole, you're not ever getting any, because that is never going to be facing the sun. However, that tilt stays there as the sun travels around the Earth. So by the time it's other way around, the Earth travels around the sun. By the time the Earth has got around to the other side of the sun, the tilt is now back to front. So if you imagine instead the sun coming from the other side, so coming in from the left of this Earth for a moment, now the southern hemisphere is getting most of the energy and the northern hemisphere is not getting much. And so we have the opposite. We have the summer on the southern hemisphere and the winter on the northern hemisphere. So the seasons is purely based on the tilt of the Earth. Right? It happens to be tilted. If it wasn't tilted, if the axis was perfectly up and down, perpendicular to the sun's rays, then there would be no seasons. It would just be a constant temperature year round. But seasons are good. They allow for various life processes to go on. And that is all the theory content for this lecture. As usual, there will be a couple of questions. I think there's only 2 for this one. So there will be a couple of questions. I'll do a separate video for those and they'll be up shortly. But take the time to read through this. Make sure you're happy with the concepts presented here. And I will see you at the next video.